Yeah, all right. Sorry about that. As I was saying, so the motivation here comes from clustering on graphs as a general task. And I think whenever we think about this, at least on a higher level, I think we tend to think of this separation into, say, 2 or 3 or big, large groups of nodes in which we'll have this very clear separation, right? And this can be seen on some synthetic data or some real world data. In that case, what we have here is a graph of all senators in the period between the 1700s up until 2008. And the edges between 2 senators are set if those 2 senators have voted on the same bill within a span of 2 years. So here what we have is a nice bipartition right around the end of the American Civil War. So the one in yellow are the ones before, and all the ones in red are the right after. And we can also see this sort of similar behavior even with synthetic data. However, whenever we're talking about real world graphs, especially large graphs, it seems that they lack these nice global properties, but instead they also showcase these nice, say, rich and local structures. So we saw some of these examples yesterday on Mario's wonderful tutorial, and we have the protein-protein interaction graph. I don't know if you can see here, but if you zoom in on one of these particular structures here, especially at the fringes, you'll see that they all neatly cluster into some sort of set of proteins that exhibit a similar functionality. And the same thing applies, say, in this Facebook friendship graph here, in which in this part here in red, we can see, say, all the students of the year 2008. So although the graph itself may not exhibit those very, say, global properties, we could also have these local structures that are also very rich. And these are the ones that we'll be focusing on finding. So our goal is to detect those small-scale clusters. Or one distinction that is important to make here is that we're focusing on one particular structure. We're not trying to detect all those different types of local structures rather than one in particular. And for that case, we're assuming to have a small set of seed nodes that take part into that cluster. So our goal is to find the actual cluster that also contains this set of seed nodes. So this is more or less the goal of local graph clustering. So if we're formalizing this goal a little better, we'll assume to have been given a graph, a set of vertices and edges, and a set of seed nodes. And it's going to be a strict subset of the set of vertices, and it's going to be much smaller than the overall number of nodes here. Typically, in this case, we're talking about very large-scale graphs, and we only are given a very small number of seed nodes here. So our goal is to find this good cluster that contains S, and for that, we need a very good local clustering algorithm. And in this context, good means that it's, first of all, it's local. That is, the computational time only depends on the size of the output and not the size of the entire input. Here, we're not focusing on processing the entire graph because that would have been too expensive. Also, it has to be simple, easy to implement, and easy to interpret. And it also has to be tight. That is, it has to have good recovery or approximation guarantees. So in this context, there is a lot of work. This has been an active field of research for, say, the past 20 years or so. But one thing that I'd like to mention here, which is what we can call it the limitations of local graph clustering, is that nowadays we have a lot of graph data sets that not only contain the connectivity between nodes, but they also have some additional information, which can typically come in the form of, say, node attributes. So if we go back to the example of this Facebook friendship graph, we may not only have the connectivity between each of these users, but those users could also have some extra information, say the user's age, location, or for that case in which, say, the red nodes are the students of 2008, and say that that would be our specific target that we're trying to recover. Imagine if we would have, say, the graduation year of each of those students. Imagine how useful that would be in the sense of the recovery of that particular cluster. However, most of the existing local graph clustering techniques, they only exploit the connectivity of the graph. So our question here is how to incorporate this additional information. So if we revisit this goal that we had in mind here, the only modification that we do here comes in the form of these so-called noisy node labels. And we're going to talk about this in more extent. But this is how we incorporate this extra piece of information into our framework. So one thing that I forgot to mention is that among all these different techniques here. The one that we'll be focusing on particularly for at least this presentation and the majority of our work is called flow diffusion, and we're going to go over it. But keep in mind that the same technique could also be applied to other local graph clustering techniques, and in fact, we do so in the appendix, and we also show that it works. But talking about flow diffusion particularly, so most of local graph clustering techniques, they are based on some form of diffusion. Diffusion here meaning having, say, a quantity that we can think of it as an amount of mass that is located in the seed nodes that we have, and it dispersing this amount of mass onto their neighboring nodes and so on. The same thing applies here for flow diffusion. We don't have much time to go over the actual algorithm, so I prepared just a simple setting here where we just can go over the high-level concepts of how this works. So let's imagine that we have this graph here on the right, and our seed node here is node number 4, okay? So to initialize this algorithm, we give this number, or at least the seed nodes, we give them a certain amount of mass, and all nodes in general have a certain amount of mass it can contain. This is called the sink capacity. So this whole process starts because the current mass that the seed node's holding is greater than what it can retain. So whenever this happens for any node during this algorithm, this is an iterative algorithm, we'll pick one of those at random, one of those nodes that exceeds, whose mass exceeds its capacity, and this is what we're going to do. Essentially, we're going to disperse the excess of mass to its neighboring nodes. And this is going to be done proportional to each of those edge weights. So if we have an unweighted graph, for example, this is just going to be uniformly distributed amongst the neighboring nodes. And this whole process continues because keep in mind that, say, the amount of mass node 3 receives could be also greater than its capacity. So in the next iteration of the algorithm, this could be a node that we can pick and also distribute its mass, and this whole process continues and so on. So this whole process continues until we either reach a state of equilibrium, or typically when we exceed a certain number of iterations, to which after we obtain an output cluster, which can then be post-processed, then that would be the indication of the cluster membership. And keep in mind that this is all local because we don't have to explore the entire graph. This all is contained around a certain region around the seed nodes here. Okay, now that we talked about the general process of, say, flow diffusion, how do noisy labels, what are these in the first place? So these are nothing more than a way that we model this external source of information. Conceptually, those could be thought as just binary indications of the cluster membership. And they are noisy because originally we can just think of them as just ground truth data, but what we do is that we take a fraction of them and flip them, and this is how we introduce label noise. And this proportion of flipped labels determines the quality of data. And why do we do this? It's because previous works that also try to incorporate this extra source of information, if any sort of abstraction is not made on those, say, node features, we'll have to introduce extra assumptions on how this data is distributed if we're talking about some recovery guarantees. And this is our way to avoid that, because if we abstract all these sources of information as noisy labels, we remove all the assumptions of the data distribution over the node attributes. And for those who may be thinking that this is not much connected to practice, from a practical perspective, we can simply see those noisy labels as just a result of applying an imperfect classifier over just the features, trying to determine that cluster membership, that cluster that we're trying to recover. Okay, so now we revisit the whole framework that I was just describing using flow diffusion, and then we can see how incorporating these noisy labels can be helpful. So here we have our input graph again, our seed nodes, and now we also have those noisy labels that we call them YIIs here. And informally, what we do here is the following. We apply a reweighting scheme to each of the edges. So here only for the existing edges, of course. So say that we encountered an edge, what we do is the following. If the nodes that take part in this edge have labels that agree with each other, we just keep it as is. But if the labels disagree, we reweight this edge and set this value to epsilon to something that is much smaller than 1, for example. And then what we do is that we run local graph diffusion on G prime, starting from S. So one caveat here is that this is, of course, this is an informal way of describing this algorithm, but this is all local. It does not require for you to first reweight all edges, or first obtain all noisy labels, reweight all edges, and then run the local graph clustering algorithm. This could still be done, say, online. As we explore, as we execute local graph clustering, those edge weights could then be determined, and then local diffusion can just be executed. So conceptually, how can we think of this reweighting scheme could help? So I just brought a little example. So say that this is our input graph, and in red you can see our seed node. This is in the target cluster that we're trying to recover is the upper right part. You can see that this graph structurally is not very informative. So say that if we were to apply flow diffusion, as we were just seeing, and dispersing this mass, we would have very little hope of accurately recovering the target node, either at the expense of, say, some false positives or some false negatives, which is something that we're trying to avoid here. But say that we are also given some noisy labels, which actually agree with the cluster that we're trying to recover. Now, if we would leverage this information and apply the reweighting scheme, what we would actually be doing is injecting information and reshaping the graph such that we will have higher hopes of recovering the target cluster accurately. So since we're talking about recovery, and we also talked about the good properties of local graph clustering algorithms, we talked about the local aspect of it, hopefully that it was also a simple algorithm to implement and simple to understand. We also can talk about its good properties, its tightness. And for that, we use this local random model, which is comprised of this one-sided stochastic block model, in which we'll have a set of seed nodes, and we also have this target cluster K here. And to construct this graph, we propose the following. We simply, for two nodes I and J, in which I belongs to the target cluster and J belongs to the target cluster, we draw an edge with probability P. And if we have I belonging to the target cluster and K not belonging to the target cluster, we draw an edge with probability Q. And all the edges that are outside, say we're not even talking about inter-edges, both nodes are outside the target cluster, those could be modeled arbitrarily. This is essentially our random graph model here. And the structural signal is some sort of measure of how good or how tightly connected this target cluster is. So this is nothing more than for a given target node, a node that is in the target cluster, this is nothing more but the ratio of average ratio of nodes that are neighboring nodes that are inside the target cluster divided by the ones that are outside. And we also have these noisy labels. And again, there's just going to be binary nodes indicating cluster membership, one if it belongs to the target cluster, 0 otherwise. And for that, to measure its strength, we have the simple label accuracies. So if we're talking about the recovery guarantees, the first thing that we assume here is that the target cluster is somewhat well connected. And let's begin, say, with the just diffusion on the original graph, no reweighting scheme whatsoever. Here we're talking about so this is the C dagger, here is the output of diffusion on the original graph, and here this is the F1 score. And you can see that it's just bounded by the structural signal of the graph. Now, if we incorporate also this information of the noisy labels, we can introduce these extra quantities that also govern the recovery of the target cluster here on top. So asymptotically, just to give you an intuition on how this would be helpful, let's say that we had, say, perfect recovery. We had perfect labels that would indicate membership. So in this case, this quantity will be 0, this quantity will be 0, and this quantity will also be 0. So we will have perfect recovery, just to give you an intuition on the direction in which this could be helpful. Now, we also have comparisons. We have some synthetic experiments I don't have much time to talk about them, but I do have them here in case you have any questions. But I also brought some comparisons that we have done with real data sets. We have the co-authorships graphs, as we also seen in the previous talk, which is also very helpful. We have co-purchasing networks and citation networks. Co-authorship networks, essentially, we have the nodes representing authors. They're connected by edge if they have co-authored a paper. The clusters indicate the researcher's primary area of field of study, and the features are keywords. Those are the features that we're going to be using to train a classifier, and then using that to produce our noisy labels. Co-purchasing networks, nodes represent products, edges indicate if those products have been frequently bought together. The node clusters represent categories, and the features are just product reviews, essentially textual description of those products. And finally, citation networks. We also have nodes representing papers, and the edges indicate citations between them. We make them undirected. And also, the node clusters represent the paper's primary area of study, and the node features are derived from the paper abstract. So this is essentially our main results in the paper. It might be a little hard to see. So I've taken the liberty to just extract one of those examples, the one on the top left. So this one is a co-authorship network. And we have, this is the amount of supervised data points here. So say we have 5 positive nodes and we have 5 negative nodes. So 5 positive nodes could be seen as the 5 seed nodes that we have to start with, the ones that we know that are positive. And then we have 5 extra nodes that we know that are not part of our cluster. And this is what we use to train a very simple classifier. We simply just use logistic regression over, say, the binary encoding of those words for the co-authorship network. And those are the ones that produce our noisy labels. So in black, you can see the performance of the classifier as we increase the number of supervised data points, something very straightforward. And in red, we can see just the performance of flow diffusion without any reweighting scheme. It is increasing because we're increasing the amount of positive points as well. So we have more seed nodes to begin with the diffusion process. So it also increases. The one in green is our previous work. And the one in blue is the one that our work, this current work, in which it leveraged both sources of information, which we can see that combined are much stronger than each of the individual parts. And in general, we can see improvements as high as 13% against any other method in all these settings. Of course, some of them are harder to see. I selected one that we have a very clear distinction, but in general, they perform much better than any of the individual parts. It's pretty much it. If you have any questions, I'll be happy to take them if we have any time.
Thank you, Artur. In light of the technical difficulties of the coffee break, so we have time for some questions.
Thanks for your talk. Where do the labels come from?
So you're talking about the real world example or even in a practical setting?
No, about the fact that you have a classifier.
Mm-hmm.
Where are the Y variables?
Okay, so in this case, we assume we have this is an attributed graph, right? We assume to have a very small number of ground truth examples. The ones that we know that belong to the target cluster, and ones that we know do not belong to the target cluster. This could be as little as 5 each, okay? Yeah. And then what we do is that we train a classifier on top of that, and this classifier is the one that produces the noisy labels.
Yes. Thank you.
Any more questions?
I have a comment, which is it working?
Yeah.
Okay, right. So I mean, it's about the reweighting part.
Mm-hmm.
We're working on this now, and in the past there've been, of course, other attempts. Perhaps as a general encouragement, it's a good practice to do that. I mean, we're finding that it can really improve the performance of any algorithm, really. So keep this in mind. So it's another way to squeeze a bit more from your data. So even if you apply your method on the initial say, unweight the graph, but even if it's weighted already, you can do reweighting in a smart fashion, and that should make the classes more visible. So, let's say, so this, of course, was applied in this context, but in general, as a recommendation, is kind of no problem. We should have soon a paper about this. Thank you.
So let's thank Artur once again for a nice talk.
Thank you.